Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture called Green's Functions for Initial Value Problem. When last we met, you were solving this problem for y sub p. I hope you finished it, but maybe you didn't, so if not, here's another chance. You know what to do. Let's see how you did. Well, f of t in this case is e to the 2t, and we found that y sub p was this, the integral from 0 to x of the hyperbolic sine of x minus t times e to the 2t dt. Now, if we were just talking about a math solution, we might stop there, but we're engineers in training, and engineers have to get answers to the problem. And so we're going to have to finish the integration. So the best thing to do here is to write what the hyperbolic sine is in terms of the exponentials and use properties of exponentials, and realize that x is a constant when you're integrating with respect to t, but it's also the top limit of the integration. So I can pull out an e to the x and be left with this, and I can pull out e to the minus x and be left with this, and finish the calculation realizing that e to the 0 is 1, and it's going to be e to the 3x, and there's going to be constants. So you should have gotten this as your answer. Please make sure you can do problems like this, because I will be asking you to do problems like this. Now here is another problem. This has a different left-hand side, but still we're finding y sub p because these are the 0 or homogeneous initial conditions. You know what to do. Let's see how you did. Well, this homogeneous equation gives rise to linearly independent solutions of cosine of 2x and sine of 2x, and the Wronskian of that is 2. So we can compute the Green's function using the formula, and we can use this trig identity over here. The 1/2 is in the denominator already, so we can use this trig identity applied to here to conclude that this is really 1/2 sine, not hyperbolic sine, but sine of 2 times x minus t. Also, our initial point was x0 was 0, and our function was just f of t is equal to t. So our particular solution is going to be, we integrate that. This is going to involve integration by parts, and you're going to use that trig identity again, I guess. Actually, maybe we shouldn't have done that to start with, but anyway, we're using that trig identity again. You pull out the x because that's constant when you're integrating with respect to t, and you should really do these calculations, and we integrate by parts here, and we integrate by parts here. We get this, we complete the calculation, and we get y sub p is equal to this. Now here's a full initial value problem for us to solve because we have non-homogeneous initial conditions and we have a non-homogeneous equation, but we'll break it into pieces like we've been doing for the Green's function. You know what to do? Let's see how you did. Well, the solutions to this are going to be c1 cos 2x plus c2 sine 2x, but now we're going to use these initial conditions to solve that, and so we will get this is my homogeneous part of the solution. But now we're going to solve the one associated with y sub p. Well, we've already found the Green's function of this, so all we have to do is substitute this being the new f of x. So let's do that. And in fact, we've done, there's the new f of t right there, and so we have to do this calculation. And this integral is one you should know how to do. This is something you studied in Calc 2 at the College of DuPage, is using this identity. So we do that, and we do the calculation. Again, you should verify all of these steps. It's good integral practice, and one day I will ask you to do this. get this, and this is your y sub p. So that means we add those two things together, collect like terms, and do the simplification, and this is my solution. Now the beauty of this is that we can immediately write down the response of a system if the initial conditions remain the same, but the forcing function is changed. And we've seen that here. And in fact, if we change the problem to be this with a different initial condition, what we could get is this could be the solution that we end up with. And again, this is another one for you to practice. Okay, now we also can look at things where there is a piecewise f of x. We're going to break this into different parts as we integrate it. And you can think about this as being something where there wasn't anything and the compressor kicked in for a while and the compressor shut off. That's the way my air conditioner works at my house. So anyway, this is what you want to do. It's a piecewise function. You know what to do. Let's see how you did. Okay. So f of t now has three values depending on what is happening. If for x less than 0, it's always going to be 0 because that function is 0. Between 0 and 2 for x, we're going to have this because that's what happens while the compressor is running. And we've already solved this one too and gotten this solution. Now, if x is bigger than 2 pi, we'll get this and we'll get some more. Now we're integrating something that's 0 here, but when you integrate 0, you do get something more. And so you should check this solution, and we get this for my y sub p, and when I simplify it, I get this. We use some trig identities and so on and so forth here. So we'll have minus pi over 2 cosine 2x. So you see yp is going to be 0 to start. It's going to be this, and then in the third place it's going to be this. And so that's what we get. But then we add the y sub h to it, and we get these are all of our pieces. And these are shown as different colors. So here's what the solution looks like until the compressor kicks in. Then that's what the solution looks like while the compressor is running. And after the compressor is finished, this is what the solution looks like. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless.